but let me already use the opportunity to thank the organizers, in particular Renate and Frank, for inviting me. Also Timothy for last-minute help with the computer system, which I hope is going to get started now. One slide up. Can I do this? Oh. At any rate, so it's quite ironic because this is the first time I'm speaking at a conference for quantum gravity explicitly, and I think I spent most of my career working on aspects of quantum gravity, but now in the last 3 years or so I turned my attention first time to classical gravity, and as a matter of fact I think also for the first time in my career I have computed things which are actually measurable, and I must say it's a lot of fun. So I'm going to speak about high precision classical gravitational wave physics from a worldline quantum field theory, and that's based on a series of papers I've been working on with a great group of collaborators back in Berlin, namely Gustav Ure Jacobsen, who is a long-term postdoc financed through our RTG, and 2 PhD students. Gustav Mogul is the long-term postdoc, and Gustav Ure Jacobsen and Benjamin are both PhD students. The first Gustav just graduated, and we've also had some papers together with Jan Steinhoff from the Albert Einstein Institute, who brought in the gravitational wave expertise into our group. So let's just start, and that was why we fought so hard for this computer setup with Timothy to get this movie going. So with this little movie, I want to show you sort of the content of my talk. These 2 black dots here, you can think of them as 2 black holes which are flying past each other at, 40% of the speed of light somewhere in our universe, and because their masses are being accelerated, they emit gravitational waves. And the goal will be to compute both the waveform, that is the far-field waveform, which is the thing we can in principle observe in gravitational wave detectors, although of course the 90 or so events that we've seen so far originate from bound state systems, so mergers of 2 black holes or neutron stars which encircle each other for a long time and then fuse. And the second observable that one can compute, and that's what I'm going to put a lot of effort in, is essentially the scattering angle. So the change of momentum from initial to final states in that process. And then we'll also look at spinning degrees of freedom. So we'll also look at the change of spin in that setup. So why is this interesting? Why is this relevant? Well, first of all, we have to provide very accurate waveforms for the new generation, the 3rd generation of gravitational wave detectors, which are scheduled to go online in the 2030s, and they will increase their sensitivity by a factor of up to 100, and also extend the frequency range of their observations. And that entails that the present state of the art of the predictions from the standard model of gravity, Einstein's theory of gravity, are not sufficient, and we have to go well beyond the existing predictions. Of course, in doing so, very similar to high precision studies in quantum field theory within the standard model, this, the justification for doing this is to perform high precision tests of our standard model. So Einstein's theory of gravity, testing it in strong field regimes. We can also study questions related to black hole formation and populations. Of course, neutron star properties are also hiding here, and potentially one may even be able to see signals beyond the standard model. As I said, to date, some 90 such merger events have been observed in the LIGO, Virgo, Kagra observatories, and these are plotted here in this very nice plot where you see the solar masses of the 2 constituents and then the emerging fused higher massive black hole or neutron star that emerges. So, as I said already, the 2 main players in this scene here are black holes, which of course are only characterized by their mass and spin, as well as neutron stars, which have more degrees of freedom, a radius, tidal deformability parameters, and so on, which are the highest density mass object in the universe, and they serve as sources for these gravitational waves. The situations that we have been able to observe so far are the bound state situations where we have a very long and spiral phase, sort of this blue phase, in which continuously gravitational waves are being emitted. That's why the frequency rises. They come closer and closer to each other until they merge and then ring down into a stationary phase. Our work is focusing on this in-spiral phase, which is the longest phase in the history of that system, in which weak gravitational fields apply, and a perturbative setup where you look at the metric tensor as a fluctuation about flat Minkowski space is the correct description. And this is, of course, exactly the setup that we've been studying for many years in perturbative quantum gravity, and sort of that connection is the base of our approach to use these developed techniques to study perturbative quantum gravity now for the classical system, for the classical two-body problem. And a particular incarnation of that is the worldline quantum field theory approach, which I want to introduce to you. So just as in the Newtonian case, the general relativistic two-body problem comes sort of in two flavors, either the bound or the unbound state. For the bound state, the natural expansion is actually not just in Newton's constant g, but due to the virial theorem, this is linked to the velocity. So one does a so-called post-Newtonian or non-relativistic expansion here, which goes in powers of g and v squared. In the scattering scenario, which is the scenario I want to focus on, you can work exactly in the velocity and just expand in weak fields, so essentially in a power of g expansion, which one calls the post-Minkowskian expansion. This latter thing is, of course, the situation which is closer related to quantum field theory, where the scattering experiment is sort of the paradigm of all our descriptions. And I will focus exclusively on that case, and then the end comment on how we can use results from here to also infer information for the bound state system. So how would you set up such a problem traditionally? Well, first of all, we need a description, an effective description of the black holes or neutron stars. And as long as they are well separated, meaning that the separation of these two objects is much larger than the intrinsic sizes, so the Schwarzschild radius of the radius of a neutron star, a point particle approximation is a good first order description. So we just have the point, I'm missing the mass term here, the point particle, and that is coupled to bulk gravity plus some gauge fixing constant. Now what you would do, you would look at the equations of motion, so these are Einstein's equations and geodesics equation, and then set up to solve them perturbatively. As we're looking at the scattering scenario, we would start out with a zeroth order situation where we just have straight line trajectories. So this would be the blue trajectory here. And then you systematically, in a G expansion, compute the deflection corrections. And of course, on the gravity side, you start out from Minkowski space and then compute the emitted radiation also in powers of G. However, you might not be, or you certainly are not interested in the exact trajectories and also the gravitational field everywhere, but you're interested in the far field waveforms, so the 1 over r part of the metric, so this blue tensor here. And also this would be what I showed you at the beginning, these, the waveforms emitted. And then also in the dynamics, so the impulse, the change in momentum is an interesting observable that you want to compute. Now, the way we approach this problem is by translating this perturbative solution of the classical equations of motion to a diagrammatic problem in a sort of hybrid quantum field theory, which has a worldline part described by one-dimensional QFT, which describes the black holes and neutron stars, and the bulk gravitational action. So one simplification that you can do, you introduce an Einbein on the worldline and go to sort of a Polyakov type formulation of the problem to linearize the coupling to the metric and the graviton. So that would then be the leading description. But of course, there are more degrees of freedom, finite size effects, but in particular spin effects. So you would want to also describe the spin of the black holes or the neutron stars, and then also tidal deformabilities. And I'll tell you in a bit how you sort of augment this worldline action to also capture the first layer of these effects. Now, in our WQFT prescription, what we do is we, of course, make the same ansatz of a deflection and a gravitational fluctuation about flat Minkowski. But then we perform a quantization of these blue fields, so of Z and H, and just look at the tree level contributions to the one-point functions. Because the one-point functions, the vacuum expectation value of H and of Z, solve the classical equations of motion in this particular background, the straight line background, and that's all we need in order to set up a systematic expansion, and we can also directly focus on the observables we're interested in. In doing that, we can port advanced quantum field theory techniques, in particular multi-loop integration technology, to this classical gravitational physics problem. So let's have a little bit closer look how this perturbative setup looks at. So as I said, we have these two quantum or fluctuation fields, the blue ones, Z and H in the problem. For the worldline, we have quadratic, we have a second order time derivative here, so that's why we pick up 1 over energy squared, omega squared propagators on the worldline. So these are the worldline fluctuations. And then in the bulk, of course, we have perturbative quantum gravity. So we expand out the Einstein-Hilbert term in this weak field approximation. We pick a gauge, the gauge, and then, of course, you start out with the well-known graviton propagator right here, and you have an infinite series of graviton interactions in the bulk. One important technical detail, which I don't have time to get into in these 30 minutes, is that the nature of the problem forces us to work with a Schwinger-Keldysh type or in-in type formalism, because we have dissipation. When you have the ingoing situation, you have no gravitational waves and you have no Z. However, in the final state, it's clear that you have shifted, so the deflection Z does not decay to zero at infinite times, and also you've emitted gravitational waves. So you don't prepare the in and the out state, but you only prepare the in state and you want to know the outcome. So at the end of the day, all that happens is that you're advised to take retarded propagators instead of Feynman propagators, and you can work with the standard Feynman rules you extract from this description up here, but there's a longer story in order to prove that that is correct. But in hindsight, you could argue it's obvious, because all I'm doing is I'm just setting up an efficient way of solving equations of motion, the classical equations of motion, and there, of course, I would always use, for causality reasons, the retarded propagators. How can we now include spin on the worldline? And there we have a very nice description, which actually is inspired by string theory. Namely, we capture the spin degrees of freedom of the black holes or the neutron stars by adding anti-commuting fields, vectors, on the worldline. And if you take n flavors of these, you are able to describe up to spin to the power of n interactions. And it turns out that at least up to n equals to 2, which allows you to describe spin-orbit and spin-spin interactions, the resulting theory is an n equals to 2 superparticle coupled to a curved background. And that is exactly this blue theory here, which I'm writing down. So the black and the blue together are exactly the n equals to 2 superparticle action with fixed coefficient here for the r psi to the 4 term. And these psi's encode the spin tensors of the black holes and neutron stars as follows. So the spin tensor is just given by essentially this bound state of psi bar psi. So I'm now working in n equals 2, so these are now complex fermions, and the i's denote they count the black holes, black hole 1, 2, etc. Now, at this layer, when you go to spin squared, for the first time, you see a description, a difference in this description of a Kerr black hole and a neutron star, and that is this red term here, which comes with a free Wilson coefficient, CE, which distinguishes the neutron star from from a Kerr black hole. A black hole has E is equal to 0, and a neutron star has some value of CE, which will be one of the things we would like to measure. Of course, you can now feed in this description in the same logic of this background field expansion. So for the spin degrees of freedom, we have a constant piece, which a constant psi, and then a fluctuating one, which we want to integrate out, which now has a linear propagator on the world line. And the background blue psi encodes the initial spins of the two objects. And now we can also compute the spin kick, namely the change of the spin after the scattering process. Then tidal interactions would be the next layer. So I just flash them here. You get two Wilson coefficients which couple to the electric and magnetic curvature in that sense. And again, these are intrinsic quantities describing the neutron stars. So I talked about the propagators. Let's have a look at the vertices. First of all, it's important to note that we have a sort of hybrid QFT here, because we have all the worldline degrees of freedom which live on this one-dimensional worldline, and we have the four-dimensional bulk theory. So we will have vertices which just live on the worldline, and we will have vertices which live in the bulk. The vertices in the bulk are the standard perturbative corner gravity vertices. The vertices on the worldline have a lot more structure, and they actually at least if we start including spin, can couple an arbitrary number of gravitons to the worldline and an arbitrary number of worldline fluctuations, which can be both Z and psi, so you can actually compactly pack them into one superfield in order to describe it. So the coupling is scales with square root of g to the number of gravitons. And importantly, that's, I think, the most important thing I want to convey here on this formula is that you only have energy conservation on the world line. So just a one-dimensional delta function opposed to, of course, a four-dimensional delta function in the bulk. And that fact leads to the situation that although I only want to compute tree-level amplitudes in this theory, I still have non-trivial momentum integrals to perform. So loop-like and momentum integrals, just because I do not have full momentum conservation on the worldline vertices. So the sort of three spatial degrees of freedom of the momenta on the vertices are still to be integrated over. That is why at higher and higher orders in the post-Minkowskian expansion, you encounter more and more complicated loop integrals, which are of a very similar type to the ones you encounter, say, in the standard model or QCD. Right. So for the bulk, as I said, it's what we know and love, higher and higher orders in the gravitons. There was a talk yesterday by Michael Ruf, I don't know if he's in the audience, and he said this is not tractable. I would strongly disagree. This is absolutely tractable at a given order in the PM expansion. This is manageable, and of course you need computer algebra systems to deal with it. Good. So let's look at the observables that we can compute in WQFT. The first one I want to focus on, and that's where most of the work has gone in the community, is the impulse of a change of momentum of that scattering process. And translating this to the worldline QFT language, what we want to compute is the one-point function of x dot, the difference at tau is equal to infinity and minus infinity. We can, of course, write it as an integral over the acceleration. And after Fourier transform, you realize what you want to compute is just set of omega in Fourier space, in energy space, in the limit that omega goes to 0, and you sort of cut off the final propagator. So diagrammatically, what we want to compute are all these diagrams with one outgoing worldline fluctuation line with 0 energy. And in these diagrams, the dots always denote sort of a background, so black hole 1 and black hole 2. And I have to sum all possible diagrams that contribute at a given order in G. So at linear order, it's very simple. We just have a single graviton exchange. At 2 p.m. order, we have these graphs. At 3 p.m. order, we have already more. And state of the art is G to the 4. For the emitted waveform, that was the little movie I showed you in the beginning, the leading order contributions, I mean, here you just need to compute all diagrams with an outgoing graviton line. I'm missing an equal sign here. This is the first contribution. And that was, these three innocent-looking diagrams were the basis for this little movie I showed you, which give you that at leading order in the D expansion. I should say that this computation without spin was first performed in the 1970s by Thorn and others, but in 3 very long papers. In our approach, it's a rather streamlined and short computation, and we were also able to update it to spin, which hadn't been computed before. And then in principle, you can also find the full trajectory, but as I said, you might not really be interested in that. So how do these computations look? So they become at higher and higher orders in the PM expansion, of course, more and more challenging, in particular from the side of generating the integrand, but even much more in the challenge of performing these loop integrals. And this is really where the Feynman integral revolution that happened in the last decade or so in quantum field theory really can be brought to use in order to access this problem. So here's sort of the workflow of such a high order PM computation. So the first step is that we need to generate the graphs. We have the Feynman rules, and this we do with a sort of recursive Baron-Skeeler type approach, because we're just looking at tree-level diagrams. So that's not too hard. Then we insert the Feynman rules, and then extract the tensor integrals we have to do. Was there a question? No, sorry. Right. Which need to be tensor reduced to scalar integrals. And after that process, I can just give you a glimpse on what the structure of these integrals is we have to perform. So if we're interested in the n-PM order, we're looking at single scale n-1 loop integrals. So at 4 PM order, which is the domain we just reached, we're looking at 3 loop integrals. And they have a peculiar structure that there's just one-dimensional quantity appearing in them, which is Q, the momentum transfer, which you can scale out. So that's this outside Fourier transform you have to do. And then you have these n-1 loop integrals, both over graviton propagators and worldline propagators, so sort of linear and quadratic propagators, and a bunch of delta functions, which tells you sort of in what mass sectors you are in. The important thing is that the blue integral that remains depends on a single parameter, gamma. This is the relativistic gamma factor in this scattering process, and that is very helpful in order to then solve these integrals systematically with the so-called differential equation method. So at 1 PM order, the single graviton exchange for problem is trivial. We just have a pure Fourier transform, and you get sort of this scaling in the masses Ng. At 2 PM order, you have a one-loop integral to perform, and you have this mass sector and the mirrored one. And as a matter of fact, also these two contributions are completely captured just by the solution of a geodesic equation. So all terms which go linear in M1, say, and arbitrary powers in M2 can be deduced from the solution of a geodesic equation. So new challenges arise at 3 PM, at 4 PM, where you go beyond that. But I didn't want to show you these integrals here. So right. So once you have reduced to these scalar integrals, you have to find a set of master integrals, a basis of master integrals for the techniques of so-called integration by parts, which have to be updated to the retarded problem we're looking at, because they were, of course, developed in particle physics or in collider physics for Feynman propagators. Once you have these master integrals, you solve them by the method of differential equations, which essentially uses a differential equation in the single parameter these masters depend on, and then after you have to still fix the boundary conditions in these differential equations by using the method of regions, which separates then the virtual gravitons into potential and radiation modes. And then finally you find the results of your computation. So let me just show you one of these results for the impulse at 3 PM order. So the change of momentum is entirely parameterized by the scattering angle theta. It has a certain dependence on the velocities and on the impact parameter b. B is the difference of b1 and b2. And the scattering angle here, I'm showing you the results up to 3 PM order, has, starting at 3 p.m., a radiation reaction piece where really the difference between using Feynman propagators or retarded propagators comes into effect, and the conservative piece which sits here. This is dissipative because you can now add delta P1 and delta P2, and you'll see that exactly this contribution here is the source of a non-momentum conservation for these two bodies. That means that the gravitational waves have emitted 4 momentum, which you can compute for at this 3 p.m. order. And recently we updated this to the 4 p.m. Problem. So now we have we're facing 3 loop integrals, 2 integral families, certain number of masters that we have 4 sectors which we had to solve, and then you end up in quite a nice function space in which the result is then expressed after going through these steps, which now next to logarithms, dilogarithms, also feature elliptic functions in the answer. But everything just depends on gamma. So this would be here in a snapshot at the spin contribution to the 4 p.m., the spin orbit contribution to the 4 p.m. scattering angle. Here, this functions f are these function bases that I talked about before. The s plus minuses are the couplings of the spin to the angular momentum. So these are the spin orbit terms. And then there's a total number of 32 of these polynomials in gamma which appear in the answer. And the thing I separated out here is the test body or the geodesic motion piece, which you get just by elementary looking at the geodesic motion in the Kerr black hole background. And that, as I said, is now state of the art. In doing these computations, as a matter of fact, you need a lot of computer power. So that was also something new for me and a lot of fun. So for example, for the problem we just faced, we had the number of diagrams were of order 200 in the non-spinning and 530 in the linear and spin case, resulting in some 10,000 integrals you had to reduce. But you could do that by then projecting them on these number of 23, 64, 66 master integrals, and then you can complete the computation. All this is analytic using Mathematica form and other techniques. So I think I have like 5 minutes. Good. So then I can also say some words now about the waveform, the far field waveform. Just let me just talk about the leading order computation here. As I said, this would be the sum of these 3 diagrams which you have to perform. Now the integrals are more tricky. They depend on 2 parameters. That's why going to so high orders is more challenging here. Of course, also here, the motivation for doing that is a little bit less, because so far we have not observed the scattering events for the waveform emission. However, in this, from the scattering angle, for example, you can deduce effective Hamiltonians that also describe the bound state problem at high PM orders. Good. So the technology is now such that I can extract the waveform by looking at this 1-point function of h and doing sort of an energy transform, projecting it on the 2 polarizations I have for gravitational waves, the plus and the cross polarization, and then you find the explicit waveform for the result. And this was the movie I think I showed you in the beginning. So this is now the plus polarization at v is equal to 0.4 and a certain value of b, which I don't remember. This is the plot I showed you before, or the movie I showed you before. There's a very nice effect that you can also compute here. That's the wave memory, the memory effect, because the very surprising thing about GR is that if you have such a gravitational wave passing through at infinity, that if you have a flat metric at infinity, and then the wave comes through, of course it wiggles, but it doesn't settle down to the old state. But there's a memory effect, so there's a shift afterwards. And here I'm showing you now. I mean, this is really the wave memory after the gravitational wave has passed through. You saw on the left-hand side the situation. I'm looking at the celestial sphere angles theta and phi, and now this is the other guy. So it comes through and settles and then remains like that in this nice wave pattern. Okay, this is now a movie which shows you the curvature, which of course vanishes when after the wave's gone through. So the curvature comes and then goes. All right, that was what I wanted to tell you. Of course, this is such an important field that there are many groups working on this, also using different approaches. And I do want to also give credit to these other approaches. So very closely related to our approach is the worldline effective field theory approach, in particular pushed to very high orders by the group around Rafael Porto at DAISY. The distinction there is that they do not quantize the worldline degrees of freedom. They only integrate out the gravitons in their approach. But they were first to reach the 4 p.m. level, which we now also managed to, and we just finished the spin orbit computation like a few weeks ago at these high orders. Then there's a very large community using scattering amplitudes as the tool to address the problem. So in a sense, there you take, if you look at the spinless case, massive scalar fields, quantum fields, as avatars of these black holes, and extract the classical limit from these amplitudes. Of course, from the purely amplitude point of view, there are even more developed or more efficient techniques to compute these objects than in our worldline theory. However, there the challenge lies in extracting the classical limit, which becomes a lot more complicated than in our formulation, where we just have to look at the tree-level diagrams. And then there's sort of a hybrid thing known as heavy black hole effective theory, which is related to the heavy quark effective theory approaches known in particle physics. And here on the waveform side, the amplitudes and heft community has just recently updated the result I showed you to the next order, yet for spin it has not yet happened. Okay, this was and then I should also, I'm sorry, just 2 days ago when I was preparing these slides, the group of Van Hove and Damgaard and Plante published the first amplitudes-based computation of 4 p.m., including radiation reaction. So that's when and we all agree. So that is also, of course, very important that you have different techniques which are, brought to, which are performed independently of each other in order to be sure that one really has the correct results. Good. So that was what I wanted to tell you. My summary is, I hope to have given you a glimpse of worldline quantum field theory as a highly efficient quantum field theory-based technique to compute classical gravitational wave physics in ordinary GR. The methodology was that we quantize the worldline degrees of freedom. We have to compute only one-point functions at tree level, which directly lead us to the observables. We have to use the in or Schwinger-Keldysh formalism, and we can include the spin degrees of freedom, I think, quite elegantly through a worldline supersymmetry, which is also the reason why sort of our group is ahead in the spin interactions. Open problems, the next order. First of all, we need spin squared at 4 p.m. We also wanted to reach 5 p.m. in order to reach the accuracy that is needed for the next generation of gravitational wave detectors. The formalism, the supersymmetric formalism that I introduced you to right now hits a wall at n equals to 2, and we have to see how we can go to higher spin descriptions with SUSY here. That's an open problem. Of course, we want to make progress in more on the bound orbit situation, and potentially also make contact with the so-called self-force expansion, which is an expansion not in G, but in the mass ratio. Thanks for your attention.
Okay, let's take a few questions.
Thank you. Let's see if there are questions from audience here.
So let's first there and then. Yeah.
They're already asking.
Oh, they're already asking. Okay.
Okay.
Thanks. I have two questions. To what extent has there been a comparison with numerical GR calculations? And the second question was, is there any estimate on the rate that we can expect these things to occur in the universe, these scattering phenomena?
Yeah. So to your first question, sort of the benchmark for us are numerical relativity computations. I can show you one plot which sort of resolves that. Well, first of all, for the numerical relativity, the in-spiral phase is very costly, and it is. I mean, the reason why you need analytical results is because we need to set up these huge databases of waveforms, with all various different parameters for the data analysis. Now, filling these tables with pure NR computations is just way too time costly. In particular, also a long in-spiral phase. I mean, it's very good in the merger phase when the perturbative description breaks down, but in the in-spiral phase, it is much more efficient to use our analytical results. Then, what I've been talking about scattering is just starting to be looked at from the numerical relativity side. So what I have here is a plot where we did some sort of a matching procedure where we used the scattering data, the conservative scattering data, to infer an effective Hamiltonian, including spin, which you can then use for a bound state problem in which numerical relativity data exists. And here you can see, I mean, this dotted line here would be for a particular spin configuration and masses. This is the NR computation, and you can see when you go up to 4 p.m., now we don't have the linear spin results in yet, you get better and better in terms of that. So that's I didn't pay the right attention to NR. It's very important. It's sort of, I think in this science, you want from all sides, you want to just combine information from all sides. Then from the second question, this is a very astrophysics question, so I'm not really the right person to ask, but for these scattering events, for example, there is a chance that it might be detectable at LISA because it goes to lower frequencies, and that depends a lot on the sort of astrophysical scenarios, how often such scattering events happen. But I should speed up by
one quick question.
Ilma, one thing, we will need to start sharp again at 11 because we have something after this session. So just want to warn you.
Jan had a question, but I don't know if that's allowed.
But not more, I think.
Yeah, so you have partly answered it right now, but I was just going to ask how large energy is involved in this scattering in the radiation. I mean, we know with the binaries, it's several solar masses. So
how
large
much?
is
I can't give you a precise number now. No, not out of the top of my head. Yeah.
So I'm afraid we are short of time now.
I mean, we have P naught. I could just look at it and divide it by the total, but I don't know. I have never done this computation, how much percent it is. But it's a good question.
So we are short of time now, so let us break now. Sorry, what?